welcome. I'm very happy to be here and to be invited to share a bit of what we've been doing. So my topic is AI for software engineering beyond code generation, because I guess all of you know that LLMs and generative AI is changing the way we engineer software. I even said here, questioning how we engineer software. We have to rethink everything, and we have these hype topics like vibe coding, and then you give a lot of people who really are into this and they're pushing this, and they're saying you have to, this is how you will develop software in the future, and then you have other people who are really questioning what's coming out of this. And there's a lot of research also going on in that direction. We're also doing a little bit on that. But I would say, as a software engineer, there's much more than coding. There's much more that we should look at, and this is what I want to discuss today and see how we can use generative AI and LLMs in other things, in other activities that we do in software engineering besides generating code. And I want to describe two areas to you. The first one is AI-supported requirements engineering, which is kind of a no-brainer to me, actually, because LLMs are really good, of course, of working with text, and requirements are mostly, to a large degree, text-based. So we are looking into this concept of AI-assisted requirements elicitation, requirements engineering in general, but especially also elicitation. So how can we get more and better requirements? Why is this important? Well, we often see, we actually do a regular survey with practitioners where they have pain points in their requirements engineering practice. And these are all things that we actually see in practice a lot, that you have incomplete and missing set of requirements. So requirements are usually never complete, but often they are quite incomplete. And you miss important requirements that later on hurt you in your development process. Maybe you have to work with domains you're not so familiar with, or there's tacit knowledge in your stakeholders that is hard to get. The requirements you have, maybe they come from various sources, maybe they come from your predecessor, and they're unorganized, and it's hard to understand what's going on. You don't restrict the use of language, so there might be complicated sentences, and again, hard to understand requirements overall, also because of vague words that are in there. We came up with our approach is called RecBrain, which does various things. For example, it can classify requirements, it can detect ambiguities in requirements, especially it can generate software requirements. This is what I mostly will talk about. It can suggest autocomplete. You start typing something and you can say something, oh, this is probably what you mean. It can fix, or can recommend fixes to ambiguity, and it can transform it into an ISO standard compliant template. To do this, we are not relying on one of the standard LLMs, not a commercial one. Here we follow the idea we want to have an open weight model. So we actually looked at various ones, and for our purposes and from the experiments, Zephyr was the best version. Our reasoning here is, in the end, what you might want as a company when you work with your requirements, you probably don't want it to have on third-party servers, so there should be a way to also host this locally. So this is one of the reasons why we looked at those, and we went into the direction of fine-tuning. Because, and we also see this then a bit explained, that this actually is the case, that non-fine-tuned models don't give us the output that we wanted, because non-fine-tuned models don't understand the concept of requirements as well. They don't really know how to formulate them. They don't really understand well what types of requirements you have. So what we did was we built up a really large database, from our perspective at least really large, of almost 44,000 requirements from various sources, from open source sources, but also from a lot of industry partners that allowed us access to it and built this database and gave us the possibility to fine-tune various models. And in the end, Zephyr was the best one that now has a better understanding of what a requirement is, how a requirement should look like, and what types of requirements you have. And the idea how this should be integrated in your overall process is, normally in requirements engineering, we say that we have these phases: elicitation, analysis, validation, right? Elicitation is you get the requirements, somehow you collect them from various stakeholders, then you go into analysis and see, okay, are they complete? Do they fit together? Do you have any contradictions? What is missing? And when you then have a set that you're happy with, you go into validation and go back to your stakeholders and maybe do some experiments and check if the requirements are really what you want. Now, our idea is you can very heavily get help from LLMs, in our case from our RecBrain model, on the elicitation side. So you can start with prompts, or maybe use existing requirements in addition to prompting, and you want some more requirements on a certain topic, give this to RecBrain. It generates new requirements. They are directly following this ISO 29148, which is where the template for good requirements is defined. It generates them directly in this format, and then you again can go into analysis. And then again have humans there. You can look at it and analyze it, and if they say, okay, no, we need more, you can go back to prompting and iterate on this. And also if you at some point be happy with the analysis, and you validate and you see problems, you again can go back to the RecBrain prompt and say, okay, this requirement is unclear or doesn't really fit to what the stakeholders need, we need to improve this. You can go on various iterations on this and use LLMs to speed up your work. To give you a concrete example how this could look like, I guess we all know nowadays how chatbots look like, so this is also what ours look like. As you can just prompt it, and here is, we're in Munich, and of course, automotive industry plays a big role here in southern Germany. I asked it, I want 3 software requirements for a car anti-lock braking system, ABS. And it says, of course, it can do this, so it gives me 3 requirements. First one is the ABS system shall detect a wheel spin and send signals to the actuators to release and reapply the brakes to all wheels except the spinning wheel, and that it shall respond in 50 milliseconds or less, and that it shall maintain communication between sensors and actuators through a CAN bus. And maybe I'm new to the business, maybe I'm a software engineer, but I haven't worked in the automotive industry, and I say, okay, what's this CAN bus? And I can also ask RecBrain, hey, in requirement 3 you gave, there's this CAN bus thing, can you explain what it is? And it says, of course, sure it can. In automotive engineering, a CAN is a control area network bus, and it's a communication system, and so on. So it can explain this. Which is also a helpful, nice way to interact. As I mentioned before, if you're not fully familiar with the domain, it can help you on that. But it can do more. One further example, maybe I want specifically safety requirements, because I have the good requirements already, but I want to see if my safety requirements are missing something. And say, okay, let's focus on safety requirements. Help me find 3 safety requirements related to ABS, and you can also do that and formulate your requirements that have a safety relationship. For example, the ABS system shall stop the vehicle within the guidelines set by the German Authority for Motor Vehicle Approval in case of a sudden brake application. It should not activate this emergency brake unintentionally, and it shall decelerate the vehicle using a combination of torque and wheel speed during slippery conditions. And now you could ask again, why exactly third one? Can you generate more? So you can go on interact, or you can take the ones you have now and go into the analysis step and discuss if with other colleagues if this is complete, and if you're happy, you can even go to the validation stage, or you go back and iterate. So is this good, what it's generating? Well, we have 2 things here on the slide that we checked for. So one is we have a validation test set, so one set of requirements that we did not use for fine-tuning, where we prompted the model and checked, compared what the model gave us as requirements to what humans wrote for requirements. And there's this Frugal score that allows us to compare on a almost semantic level between different texts, and we, from a scale from 0 to 1, we have 0.91, so pretty strong similarity to human-generated, human-written requirements. And I also gave you to check if fine-tuning makes sense. So there's quite a lot of effort, right? 44,000 requirements. Do we really need this? You also see in the table comparisons of requirements on the left that our fine-tuned model generates, on the right the untrained Cepher model that we use as a basis would generate. You also see the prompt down there. It's about an AI chatbot to help students better learn. And I think it's, if you read through them, I hope it's full, it's not too small. The left ones are much more clearly structured, easier. On the right, you have like a mix. Some of them are really good, some are complex, some are not really clear. So we see pretty strong evidence that fine-tuning makes a lot of sense here to really give this domain knowledge, domain of requirements to the LLM in that case. But of course, there's still a lot of limitations. We are still in the middle of that research. We have a 7 billion model. Maybe you want to have bigger because they're more powerful. They have maybe more domain knowledge that you could use. Also, if you're in a longer interaction, we still have the problem that sometimes it forgets already elicited requirements, so you maybe have to split it up and be a bit more careful in the process there. And of course, it's not proactive yet. You start the process as a human, maybe that's exactly what you want, but maybe you also want something like an agent who goes through your requirements and says, hey, this is problematic and maybe you can improve this, or here you missed something, in that specification. For the whole RegBrain thing that I presented before, I haven't shown you any examples, but we do this quality evaluation that's also still limited. We're in the middle of doing this. And we are specifically training it now to detect what we call requirement smells. So like code smells, maybe you're aware of that. Code smells are things in your code that are not a defect, it's not wrong, but it smells a bit fishy, it's not really right with it. And we have similar things in requirements that might not be wrong, but they might be a little bit easy to misunderstand and so on. And we also in the process of trying to find this using our RegBrain approach. We've done smaller case studies with industry partners and are now in the process of starting a bigger case study so that we can really interact also with requirements engineers in practice and see if they are more productive using this. Because of course that's in the end the goal, to help the requirements engineers in practice to become better in writing and managing their requirements. Second area I want to show you is AI-supported software architecture. So we move now from just finding out what we want to build and closer to how we're going to build this. And our basic idea is like that. So we want to go from requirements to architecture by first generating more high-level domain models and scenarios with the help of LLMs, maybe also semi-automatically refine those models, and then in the next step, generate architecture candidates, bring in maybe our own design decisions, or maybe also let them present different possible design decisions to us. Let the models also evaluate and compare these architecture candidates, and then select final architectures with a set of design decisions that we make. We are not complete on this process yet. I want to give you a first example where we have the first step here analyzed, where we were interested in how well can it generate use case models. Use case models are a more higher level structured way of representing how a software system could look like and how stakeholders interact with it. For that, we came up with this approach so that the user, in that case probably a software architect, would give the requirements text to our prompt logic layer. So we have one small software layer above the LLM, and here we use actually a standard LLM, the OpenAI LLMs via the API for the experiments we did now at least. We refine a little bit the input and give this to the LLM and get first actors, so what's the stakeholders in my system basically, back to the user. They're validating this and refining this, and then we give the input actors and requirements text again to our layer, which refines it and gives it again to the LLM. Then we get use cases for each actor that we again can refine and validate, and we give back the actors' use case requirements back to the LLM, and then gives us the complete use case model. And in our small experiments that we've done so far, with that's only a few people, we do see an improvement in how long they need to create these models. So we gave similar requirements, or the same requirements to several people, and asked them either to use our approach using the LLM or manually create use case models. And you see a strong speed up, so maybe roughly half the time that they needed to build this use case model when they had the LLM-based approach. So it simplifies and accelerates the modeling process. And also comparing what they came up with, the output is closely aligning with expectations. So if they did an LLM-based approach, it was similar to what they did manually. The only risk that we observed also by talking to the people in the experiment was that when they had the LLM, they over-rely on the output. So there's a risk, if it already looks good, that they're not checking it in detail anymore. We have a second example, so we pushed it a little bit further to the right here, where we also looked at creating architecture candidates. So we also do domain models and scenarios, but try to push it further down and have a more architecture and a more technical architecture of the software system also already generated. And for that, we relied on the approach domain-driven design. How many of you have heard of domain-driven design? A few. Okay, so not a lot. It's a architecture design method for software systems that is, I think, mostly used when you build micro-service architectures, but it's not specific for that. It fits very nicely together, but basically you start by describing what they call an ubiquitous language, so what kind of terminology you have, and then you break it down and say you have bounded contexts where you have certain terminology, and then you further break it down and talk about events that happen in the system, and that helps you step by step to create the architecture of the system. So it nicely connects from high-level domains and domain understanding down to technical architecture. So we believe it's an interesting and nice approach. It's also quite heavily used in practice, as I said, especially in microservice systems. A lot of people rely on this. And so we thought, can we support that? We came up with this structure here, this workflow that we wanted to use. So we give requirements as an input. Hopefully, maybe we use TrackBrain. We have nicely structured and hopefully mostly complete requirements that they gave in to this step. And then phase one, we have this ubiquitous language establishment. As I said before, this is the first step. We have domain vocabulary that is established and a glossary so that we know what's going on in our domain. Then we go into phase two, where we ask the LLM again to do an event storming simulation. Event storming is what usually the software architects and other software engineers would do. They discuss what events will be there in the software system and in what context can you call it and what data does it need. And so we identify events, commands, and actors in that phase. And then we go in a third phase where we ask the LLM again to identify this boundary context, so structure the big domain into areas that can be separated. And then go down in phase four, which is called aggregate design, where we have aggregate entities and invariants, which is already at more the technical level of how the software system would look like. The step just before we go into the full technical architecture, this is phase five, where we map this to what is called ports, adapters, and the infrastructure of the system. And then the last step is we get the complete domain model with boundary context, aggregates, and the architecture candidate. To evaluate this, we did a case study with a German company evaluating two of their software systems that are already existing, they're already built, and they already both are microservice systems, so they used DDD also for developing it. And we compared our LLM-assisted workflow with the actual implementation that they have in discussion with the system expert. And some key results we found is that in one of the two cases, the LLM-generated design was actually very close to the real system, so almost exactly as they also broke it down. It suggested one additional core domain encryption for that system, which the system experts actually agreed and said, yeah, that's also something that we could build in because encryption is an important separate concept for our software system. In the other case, however, we found that it didn't match as nicely, especially it went much more fine-grained than the experts did this, and they rated it as not practical. They said it was okay, it makes sense to break it down in that way, but it's too detailed to make it practical. Because there are hidden business rules, there are some couplings between different parts of the system that the LLM just could not get out from the requirements. There were more technical constraints that it was not able to detect from the requirements. So, of course, then it cannot really factor this into the analysis. So for the ubiquitous language extraction, overall the terms matched well. Sometimes they were too generic and needed some refinement to fit, but it was always in the right direction. Event storming simulation captured all the core business events very nicely, but it left gaps. And the context definition to technical architecture always created theoretically valid boundaries, but sometimes missed these practical considerations that I mentioned, that there are some couplings that you have to follow, and then if you split this up, it wouldn't make sense. So to summarize, the strength that we found was that also here, it accelerates the initial design. It covers systematically the domain. So if you have you clearly see that you approach it from various perspectives, and it gives a fresh and unbiased perspective, of course not fully unbiased, but unbiased from previous discussions of the engineers and the history of the engineers in the company. It just brings in this new view on how you would structure a system according to the requirements we gave it. But the limitations we also saw are this lack of contextual awareness of historical organizational factors that shape the architecture that was just not in the requirement. It's something you have to know from maybe the history of the software or from the expert knowledge that the people developing the system have. And so it overlooked strong couplings that are in the system that were not visible from requirements and sometimes then overly decomposed to fine-grained level. Especially on this aggregate design level, so the lowest level, or almost lowest for the domain, were not always well aligned with existing course structures. So there were some differences. So we're not at the end yet, so we don't know yet how strongly this accelerates. So we only had these discussions, but it was a strong impression that it would be helpful, but that we always need a human in the loop. So we actually added this here to our workflow, so that in every step we would include a human to check, to validate the terminology, to check the events that were generated, to check the context, and also check the aggregates that were generated. And this combination of human and the LLM, we believe, similar as in the requirements example, that we get a strong improvement and faster working with these documents. So, what have we discussed? That besides code generation, which again, it's interesting, it's an important topic, we can support many more software engineering tasks. So I think the whole software engineering process can or should be evaluated and investigated towards how can LLMs help here. And we have some evidence that it can. So RegBrain, we can support requirements engineers in generating, completing, and improving requirements. And with our architecture LLM approaches, we can support humans in creating use cases and domain-driven design models. But overall, we are still exploring mostly. I mean, we run studies, we do case studies, we do experiments. So we have some of it is already quite solid. But overall, what can really be done is exploring. And as you all know, the field of generative AI and LLMs is moving so fast that it's hard to keep track. So we need more studies. We are still working on this. But one of the key insights, I think, is, at least for now and for me, for the foreseeable future, the humans are needed in the loop. We need the humans there to check and keep them at the center and find ways to support them using LLMs. I want to thank my two PhD students, Kasra Habib and Tobias Eisenreich, and also the two master students, Nicolas Friedlander and Hussein Jusik, for doing a lot of this work that I just presented to you. I want to end with a vision, which I believe for the foreseeable future would be an interesting area, how software engineering could evolve, and I call it human-centered AI collaboration, that we have this more dedicated, I call them bots, maybe nowadays you call them agents, but I guess you get what I mean. So you have this independent agents over there that probably mostly are powered by some form of LLM that can do a specific task very well. For example, a RegBrain-based requirements bot that is really working on requirements well, and we have maybe a DDD architecture bot at some point over there, and then we have coding bots and testing bots and bots that know about continuous integration and deployments and so on, and they have the specific knowledge, maybe they're fine-tuned or we use Reg for certain things, whatever the concrete technology is. But we're actually also looking into this, find ways how they should interact with the humans, how the humans still interact, how they interact with these bots, and what the best way of working together is so that we are most productive and make the most out of the human experience also in this process. Thank you.
Thank you so much, Professor.
Do we have any brave ladies in the audience? Maybe over there? Yes, yes. Please give her a round of applause. Woo! Good morning, good morning.
Hi. No, I really liked your keynote. I actually do a lot of requirements and system engineering in my job, specifically on the cybersecurity side. So I'm definitely going to take your stuff and kind of see if we can integrate more of the AI. We're starting to do that a little bit, but I really like the idea of incorporating the AI into that whole system engineering process. So,
very cool. Thank you so much for the comment. All right. We've got a question coming from the gentleman over there. Here you go, Michael. Go ahead.
Thank you very much, Professor. I do research on software engineering and AI, and also I've been in practice of software engineering. And most of my research has been related to practice. And we are a bit troubled as software practitioners and researchers that up to now, 50 years down the road, software engineering has been a bit very problematic because of the very unstructured ways of practice. To the extent that, to this date, we have not caught the art well. There are lots of guidelines, lot of prescriptive ways of the way we should do it. The standards and software body of knowledge, all put in things to govern and the way we should develop software. But if you investigate companies, you go to IBM, you go to Google, they are all applying Agile, SAFe. It's totally different. When you go to the small companies, it's actually worse. If all of them are telling you they're using Scrum, and you try to benchmark and come up with something in common, you find it's really difficult. So in the process of struggle to standardize some of the things that we do, we find it extremely hard. Now, the new wave is coming in. We are moving towards a situation where expectation is that between 2025 and 2030, we are going to have total automation of software engineering processes. That's the expectation outside there. But we see the challenge that with the art not effectively caught, we are not yet doing it well. Failure is high at about between 60 and 70%. Now, with the introduction of AI, it has even gone worse that the persons who are developing software and attempting to use AI actually become much more slower. Are you worried that the future may be bleak given that background, especially as far as using AI is concerned? Thank you.
Thank you so much.
So I think I agree and disagree. We even did a study on that Scrum thing, for example. We looked at, I think, 14 companies several years ago who said they're doing Scrum, and we compared this to the Scrum guide, and according to our analysis, none of them were doing actually Scrum. So that is true. But I also see the different side, because if everything would be so worse, why is software so crazy successful? Software is running everything. So I believe it cannot be as bad. So maybe we're doing something right? I think one of the reasons why it is so different in different companies is also because software always has to be on the bleeding edge, right? If some new concepts come up, it always have to be implemented in software first. Maybe some things at some point go into hardware and so on. But we always have to be on the bleeding edge, and so it is maybe very hard to standardize. But that's an interesting question. So, but I think your question was, do I worry that AI does this make even worse? Possibly. I mean, the memes on vibe coding were hinting at that. So possibly, yeah, we could run into big problems if we just generate a lot of bad code. Our problems will explode because we deal with a lot of code already that is hard to deal with. But I mean, otherwise I wouldn't do this research. I also think there's a lot of opportunity that we can have to handle. I mean, also these big code bases. So we're starting just a new research project with Siemens, where they want to bring older source code in niche languages into new languages, which would be basically impossible doing this totally by hand by individual people, because it would be prohibitively expensive. But using LLMs and other AI techniques, this gets into their reach, and that could save them a lot of money, because dealing with all these old and historic languages can also be very costly. So I think AI is just a big word, and there are so many different ways how we could use it, and it's so much and so strongly evolving that I think it's hard to predict. I think we have to do it right, otherwise we can run in a lot of problems. But if we do it right, I think we can also gain a lot of benefits.
Mm-hmm. Thank you. Time for one last question, ladies and gentlemen. One last question. Okay. Okay, perfect. Gentleman over here. Right. Thank you so much for agreeing.
Yeah, thank you so much for letting me. Thank you so much again for that presentation. I came in halfway while you were actually doing this. So just a follow-up question to what my dear colleague has mentioned there. I was just going to ask, do you think that there is a place for co-interaction by researchers who are doing something similar to what you're doing from the fields of both software engineering and AI, in terms of bringing in knowledge? So that's to align towards the aspect of trying to reach that standardization he is talking about. Do you think that there is a place for collaboration at some point to be able to arrive at streamlined processes that will help to reduce those problems, for example, that he's highlighted? Do you think there is, and where do you suggest we start?
Thank you.
That's a very hard question. So on the academic side, to be really honest, I don't think we can do this. Because so far, in software engineering, in the 40, 50 years that existed, we have tried this, right? That academics come up with this great process, and we had formal process and all this kind of thing. practitioners don't care, they don't care, and they will not use it. So we can think about a lot of things. And this is also why I think the more popular ones like Scrum came out of practice, because they are doing this every day. And as I think from a lab perspective, that's very hard to grasp. We can look at it, evaluate it, improve on it, but I think a lot of it also has to come from practice. So and I'm not sure if practitioners really want a full standardization, because again, is a developer who is here at BMW working on optimizing some engine software the same as the other guy who's working 200, 300 kilometers to the west at SAP working on business information systems. Are they really the same? Should they really be standardized in a way that they do the same things? I'm not sure. I think, personally, I think we're not there yet. Maybe we need more research to better understand what the people are really doing before we want them to standardize.
Thank you. Thank you so much, ladies and gentlemen. Professor Stefan Wagner. Thank you so much. Thank you.